Hello everyone, welcome back to another lesson on sequences and series. Today I'm going to be doing some general revision on sequences and series. First, I'm going to have a look at our concept map for today's lesson, then I'm going to revise some definitions, and lastly I'll be doing some examples. Let's have a look at today's concept map. So everybody, I'm going to start by revising the definitions for arithmetic series, or rather sequences, series, as well as quadratic patterns. So arithmetic sequences, series, and quadratic patterns. Let's go to our first set of definitions. So an arithmetic sequence. This is a pattern which has a common difference between successive terms. So guys, hopefully this does ring a bell. An arithmetic sequence most important property is the fact that there is a common difference. So if I look at the pattern that goes 2, 4, 6, 8, 10, I can see that each time the difference has been positive 2, as each term has increased by positive 2. So if there is a common difference, that means that it is an arithmetic sequence. Let's remind ourselves of the general form of an arithmetic sequence. So just a reminder everyone, for an arithmetic sequence, the nth term is Tn is equal to a plus n minus 1d. A represents the value of term 1 and d represents my common difference. So again, this is what makes an arithmetic sequence an arithmetic sequence. Also, just a little bit of a reminder, if I'm worried about calculating the common difference will be equal to term 2 minus term 1, or term 3 minus term 2, but in general, I can say it's equal to Tn minus Tn minus 1. So that is the definition of an arithmetic sequence. Moving on, we're going to be talking about a quadratic sequence now. This is a pattern where the second differences are equal to each other. I'm just going to pause for a second and say that if you are given a pattern and you are not told what type of pattern it is, it's important for you to test whether the pattern has first differences, because if it has first differences, then we know that it is in fact an arithmetic sequence. If there aren't first differences, please don't stop at that point. Please test to see whether there are second differences present, because second differences being present and second differences being equal, the second difference has to be equal, everybody. This means that it is in fact a quadratic pattern. I'm going to go back to the board to revise the nth term of a quadratic pattern, but I'm also going to be reminding you on how we actually can determine the values that we have to substitute into the quadratic pattern. Let's go back to the board. So the general term for a quadratic pattern is Tn is equal to an squared plus bn plus c. Just a reminder on how to actually find the values of a, b, and c. We will take 2a and equate it to the common second difference. Then we will take 3a plus b and equate that to term 1 of the first differences. And lastly, to find the value of c, I will use my a and b values. A plus b plus c is equal to term 1 of the quadratic pattern. Cool. I hope that everyone's with me so far. So arithmetic sequence, common, first differences. quadratic sequence, common second difference. Let's look at the next slide. If I now want to define what an arithmetic series is, please make sure, everybody, that you know the difference between a sequence and a series. Let's look at the series definition. So an arithmetic series is formed when the terms in an arithmetic sequence are added together. So please don't let this confuse you, because we've got the words series and sequence in the definition. But the main difference is that the series is an actual sum. It is created when I add the values of an arithmetic sequence together. So seeing those plus signs are giving me an indication that this is in fact a series. So in a test or in an example, when you see those additions or sometimes subtractions, because if you add a negative value, it's negative, that is giving you a clue that it is in fact a series. If I were to write this exact same pattern as a sequence, I would use commas or semicolons to illustrate that these are different terms. Great. Let's have a look at the actual formula for an arithmetic series. So everyone, the two ways that I can calculate the sum of an arithmetic series are Sn is equal to n over 2 times 2a plus n minus 1d. Or alternatively, I could say Sn is equal to n over 2a plus l. Please remember that in each of these cases, a is referring to the value of the first term. D is referring again to the common difference, which we know is the main property of an arithmetic sequence. And L is referring to the last term of the arithmetic sequence if it is given to you. So if in the question you are given the actual value of the last term, you can use the second version. Wonderful, everybody. I hope that you are feeling comfortable with arithmetic sequences, arithmetic series, and quadratic sequences. After the break, I'll be jumping into some actual examples of these. See you soon. Welcome back, everyone. Before the break, I went over some definitions, but now we are going to jump straight into some examples. Let's look at the first example. So the question says, given the following quadratic number pattern, 5, -4, -19, -40. A is asking us to first determine the constant second difference of the sequence. B is asking us to determine the nth term of the pattern. And lastly, C is saying which term of the pattern will be equal to -25,939. Let's go to the first part. So A is asking me to determine the constant second difference of the sequence. But in order to get my constant second difference, I actually have to first work out what my first differences are. So if I ask myself, and I'm going to ask you at home as well, what is the difference if I'm moving from a term value of 5 to a term value of -4? You can also substitute in your D, which is T2 minus T1. -4 minus 5 will give me that the first term of the first differences is -9. Then moving on to the difference between -4 and -19, if you substitute into your D formula, you will get that there's a difference of -15. Moving on, if I want to see what the difference is between -19 and -40, I can see that there is a difference of 21 because negative 19 minus 21 is equal to negative 40. Now that I have my first differences, I can see that they are not equal, which does confirm that this is not an arithmetic sequence, but I still need to find my second differences because this is in fact a quadratic pattern. So I need to find these two differences. If I'm asking myself what is the difference between negative 9 and negative 15, I can substitute into D and hopefully everyone will agree with me. There is a difference of negative 6. So I've subtracted a further 6 from negative 9 to get to negative 15. Then from negative 15 to negative 21, I have subtracted a further 6. This means that my second difference is negative 6, and I can see that it is in fact the constant second difference. Let's move on to B. We are now asked to determine the nth term of the pattern. Just a reminder, everyone, at the beginning of the lesson, I went over the way that you find the general term of a quadratic sequence. A reminder that the nth term is Tn is equal to An squared plus Bn plus C. I'm going to write it on the board for us. So it's Tn is equal to An squared plus Bn plus C. But now we actually need to find values for A, B, and C. I'm going to be flipping through the slides so I can actually fetch certain values. But please remember that 2A is equal to my second difference. So in this case, 2A will be equal to, if I go back to the previous slide, it will be equal to negative 6. So if 2A is equal to negative 6, I can divide both sides by 2. So A will have a value of negative 3. In order to find the value of B, I say 3A plus B is equal to the first term of the first differences. I can immediately substitute in negative 3 for A because I've actually found that value. But now, in order to find B, I need the first term of the first differences, and that is negative 9. So I'm going to have 3 times negative 3 plus B is equal to negative 9. So this is going to be negative 9 plus B is equal to negative 9. If I carry my negative 9 from the left to the right, I will actually see that B is equal to 0. Last but not least, I need to find the value of A, and A plus B plus C is equal to the first term of the quadratic pattern. So I've already got my A value, which is negative 3. I'm going to add 0 because I know that B is equal to 0. Then in order to still find C, I need to fetch the first term, but luckily it's also on this slide. I can see that term 1 of the pattern is 5, but going back, you can see again the first term of this pattern is in fact 5. This ultimately means that if I take the negative 3 over, C will be equal to 8. At this point, please don't forget to conclude because I still need to substitute into Tn is equal to An squared plus Bn plus C. So Tn will be equal to negative 3n squared plus 8. Please note that I don't have anything with Bn because B has a value of 0. I hope that everyone's okay with me so far. Now that we actually have the nth term of the pattern, I can use that to solve questions regarding this quadratic pattern. Let's look at C. So we've now been asked which term of this pattern will be equal to negative 25,939. Please note that this is a Tn value because it is asking for the actual term number that matches the term value. So I'm going to be substituting in negative 25,939 n for Tn because I am solving for n. So this is going to be substituted in over there. So I'm going to have negative 25,939 is equal to negative 3n squared plus 8. I can see that it's going to be a quadratic equation because I have n squared, but I'm first going to actually carry over my negative 25,939. So it's going to be 0 is equal, oh, sorry guys, that equals looks a bit weird. Let's try that again. 0 is equal to negative 3n squared plus 25,947. At this point, I want to divide by negative 3 in the hopes that it will make my actual equation a bit easier. So I'm just going to get my calculator out. So if I say 25,947 divided by negative 3, it's going to be equal to negative 8,649. So this is going to be 0 is equal to n squared minus 8,649. Because I actually have an n squared minus an incredibly large number, I am hoping that this is dots because that will make my life a lot easier. But in order to see if it is dots, I have to see if 8,649 has a square root value, or it does have a square root value, but I want to see if it's going to be a whole number. So 8,649 gives me 93. So this is great. So it's dots. So it's going to be 0 is equal to 9 n, sorry, not 9 plus, n plus 93 and n minus 93. So n will be equal to negative 93 or n will be equal to 93. I'm going to stop everyone at this point. I'm going to ask if you think there's anything a bit weird or incorrect with what's on the board. Am I allowed to have a negative n value? Hopefully there's some shaking of heads. No. My term numbers have to be whole numbers because I always have term 1, term 2, term 3. They start at term 1. I don't have negative term numbers. So that means that n is equal to negative 93 is not a valid answer. So let's cross it out. Cool. So we know that it's the 93rd term of this pattern that will have a value of negative 25,939. Let's go on to the next example, everybody. So the first three terms of an arithmetic sequence are 2k minus 7, k plus 8, and 2k minus 1. We first need to calculate the 15th term of the sequence. Then we will be calculating the sum of the first 30 even terms of the sequence. So please, right now at this point, I'm hoping that the word even jumps out at you, but we'll get into it when I actually do B. But I'm first going to focus on A, which is calculating the 15th term of the sequence. Before I get into it, please remember that for an arithmetic sequence, I need to have my A value and my D value in order to find my nth term. If I have my nth term, then I can substitute in n is equal to 15 to find the value of the 15th term. Let's do the working out together. So the first three terms we know are given over here. But they are all in terms of k. So I actually don't know what the true values of A and D are. But in order to get to that point, I'm first going to solve for the value of k, because knowing what k is will allow me to determine the 15th term, because substituting k back into the first three terms will give me my A value as well as my D value. I'm going to use the main property of an arithmetic sequence in order to determine the value of k. I know that by definition, an arithmetic sequence has a common difference. So I'm going to substitute in these three values into the common difference expression to solve for k. I know that the common differences have to be equal to each other, so I am allowed to do this. So if I substitute in term 2, it's k plus 8. Then I'm going to subtract term 1, which is 2k minus 7, which is equal to term 3, which is 2k minus 1. And I'm going to subtract term 2, which is k plus 8. If I distribute the negative in on the left, I'm going to have k plus 8 minus 2k plus 7 is equal to 2k minus 1 minus k minus 8. Simplifying, I'm going to have negative k plus 15 is equal to k minus 9. Great. And then if I take my 9 across to the left-hand side, I'm going to have 24 is equal to 2k. And this means that 12 is the value of k. Great, so now that I know what k is, I can substitute that in to my first terms, my first 3 terms to actually find the values of them. So 2 times 12 is 24. 24 minus 7 will give me a first value of 17. 12 plus 8 will give me a next term value of 20. And then 2 times 12 minus 1 gives me a term 3 value of 23. So in this case, I can see that A is 17, and the common difference is positive 3, because each of these terms increase by 3 as the terms go on. Now I can substitute into my actual formula to determine the value of the 15th term. So Tn is equal to A plus n minus 1d. So term 15 will be equal to 17 plus n minus 1, so it's going to be 14 times my common difference, which is 3. I'm going to plug this all into my calculator. So it's going to be 17 plus 14 times 3 is equal to 59. Great. And then the last question, everyone, is to determine the sum of the first 30 even terms of this sequence. The sequence goes 17, 20, 23, 26. But I've been asked for the sum of the first few even terms. The even terms of the sequence are 20, 26, and 32, because this is term 2, term 4, and term 6. These are the even terms of the sequence. I still need to calculate the sum of the first 30 even terms. So because these are my first 3 terms of the even sequence, I have to find a new A and a new D. So my new A is 20, and my new common difference is 6. Then I'm going to substitute this all into the arithmetic series formula. So the sum of the first 30 terms will be equal to 30 over 2 times 2 times A, which is 20, plus 29, because it's n minus 1, times 6. Let's pop this all into my calculator. So I've got 30 over 2 times 40 plus 29 times 6, which is equal to 3,210. Welcome back, everyone. In this portion of the lesson, we're going to be looking at geometric sequences, geometric series, the sum to infinity, as well as sigma sums. Let's have a look at the concept map. So guys, I'm going to be going over each of these concepts, defining them, and then later on we will be doing some examples. So let's just remind ourselves about what a geometric sequence is. This is a pattern where there is a common ratio between terms. So essentially, if I had the pattern 2, 4, 8, 16. I can see that each time I have multiplied the term by 2 in order to get to the next term. So when there is a common ratio between all of the terms, this is a geometric sequence. The nth term for a geometric sequence is Tn is equal to AR to the power of n minus 1. A reminder that A is the first term of the pattern and R is our common ratio. Please remember you can find your common ratio by taking a term value over the value of the term that comes before it. Let's look at the next slide. A geometric series is formed when the terms in a geometric sequence are added together. So please be careful. There is a difference between sequences and series. Series are an actual sum, whereas a sequence is a list of the values of a pattern. So below you can see the 3 plus -9 plus 27 plus -81 going on. We know that this is a series because there's actually addition involved. But please note it could actually be written as 3 minus 9 plus 27 minus 81. So a series may also just have negative values or negative signs rather in between, because those values are still being added together. Because when I add a negative value, it still is negative. Great, let's look at the next slide. When I'm calculating the sum of a geometric series, I can either use Sn is equal to A times 1 minus r to the power of n all over 1 minus r, or I can use Sn is equal to A times r to the power of n minus 1 all over r minus 1. Please remember that this is when the ratio is not equal to 1, as this will make it undefined. Great, so in order to actually calculate a geometric series, I need my A and I need my R. Cool, guys, so I hope that everyone is okay so far. We are now going to have a look at sigma notation. So please remember that as soon as you see that sigma sign, there is most likely series involved because it is involving addition. And I know that the summing of terms is often associated with series. So when I see a sigma, I need an alarm bell to go off in my head telling me that this is a series question. Let's go back to the board. So the sigma symbol is an instruction to determine the sum of a sequence. So that's the link to your series. The use of sigma in series gives us the opportunity to add any consecutive terms in a sequence and not only the first n terms. So I could hypothetically add from the 3rd term to the 10th term. I don't have to go from term 1 to term 10. I'm allowed for the first term of my sum to not be term 1. Let's go to the next slide. So the next part of geometric series is the sum to infinity. The sum to infinity applies when my common ratio is between -1 and 1, and the ratio is not equal to 0. So essentially, it's when it is a proper fraction. When the ratio is between -1 and 1, the terms of the sequence approach 0, and their sum approaches a finite number. Please note that the most commonly used word when we're talking about the ratio in sum to infinity is that the series or the pattern converges. The pattern converges when the ratio is between -1 and 1. The actual terms themselves get closer and closer to 0, and their sum gets closer and closer to one specific value. So in other words, the sum is converging, getting closer and closer to one value. Let's go back to the board. So we can calculate the sum to infinity for a geometric series using the formula below. But let's just quickly look at what's on this slide. It says we can calculate the sum of the entire series with infinite terms. So essentially we're saying that if I were to add every single value of this sequence together, I can actually come up with a number that will express the sum of an infinite amount of terms. I can do this because the series is moving towards one finite number. So if I were to add all of the terms together, they are going to get closer and closer to one specific number, and that specific number can be assumed to be the sum to infinity. So the sum to infinity can be calculated when I have A divided by 1 minus R. So I need my A and I need my R. Please remember, I can only use this formula if my ratio is between -1 and 1 and R is not equal to 0. So only use sum to infinity if your ratio meets the requirements. Great. So everybody, I hope that everyone's comfortable with the definitions of geometric sequences, geometric series, sigma sums, and the sum to infinity. After the break, we're going to dive into some examples. See you soon. Welcome back, everyone. Now we're going to jump into some examples for geometric sequences, geometric series, the sum to infinity, and sigma sums. Let's look at the first example. So we are given the geometric series 5 over 8 plus 5 over 16 plus 5 over 32 plus going on is equal to k. We need to first determine the value of k if the series has 21 terms. Then we are going to determine the largest value of n for which Tn is greater than 5 over 8,192. Let's look at A. So we are given the actual geometric series. We want to determine the value of k if it has 21 terms. This means that n will be equal to 21 because I know that there are actually 21 terms involved in this entire sequence. I need to establish what A is and what R is so that I can work to solve for k. Luckily, I can see that A will be 5 over 8 because it is the first term. I then need to see what my common ratio is. So I need to know what has 5 over 8 been multiplied by to get 5 over 16. Similarly, I need to know what 5 over 16 was multiplied by to get 5 over 32. Hopefully, everyone will agree with me that I multiplied by a half because 5 over 8 times 1 over 2 is 5 over 16. So I have my A, I have my N, and I have my R. I just need to solve for k, and k is my Sn because this is what the sum is equal to. So I'm going to substitute in k for Sn, which will be equal to 5/8, open bracket 1 minus a half to the power of 21 because there are 21 terms, all over 1 minus a half. Wonderful, let's plug this all into our calculator. So I've got 5/8 over 1 minus a half. Sorry, the fraction didn't come there, a half to the power of 21 all over 1 minus a half. So k is equal to, if I round to the second decimal place, 1.25. Great, let's have a look at B. So I'm now asked to determine the largest value of n for which Tn is greater than 5 over 8,192. So I'm actually looking for the position of the term where it's going to be larger than 5 over 8,192. So I'm looking for where Tn is greater than this. I know that I can replace Tn for a geometric series with ar to the power of n minus 1. Luckily, I know what my a is. My a is 5 over 8. And my ratio, which we discussed on the previous slide, is a half. So I'm now going to solve this inequality. But to do that, I'm first going to have to get rid of the 5 over 8 because I'm working to isolate my n. So first, let's get our calculator. And I'm going to say 5 over 8192 divided by 5 over 8 is equal to 1 over 124. So 1 over 1024. Luckily, if I am aware of how to use prime bases, I know that 1024 is 2 to the power of 10. So 1 over 1024 is the same thing as a half to the power of 10, which is wonderful because I like to be able to get the same bases in exponential equations because then I can drop them. But I have to remember that a half is the same thing as 2 to the power of negative 1. So it's going to be 2 to the power of negative 1, n minus 1, is greater than 2 to the power of negative 1 raised to the power of 10. So essentially, my inequality will say negative n plus 1 is greater than negative 10 because I'm allowed to drop the like bases. Now solving for negative n plus 1 is greater than negative 10. I'm going to take my 1 over to the right-hand side, so it will be negative n is greater than negative 11, but I have to divide by negative 1. So it's going to be when n is less than 11. So the largest value for n for which Tn is greater than 5 over 8192 would have to be 10 because 10 is 1 less than 11. So the 10th term will be the largest value of n for which Tn is greater than 5 over 8192. Great, let's move to the next example. So I'm determined, this is the same slide, moving on to the next example. We're now going to evaluate the sigma sum where we have 8 times a quarter to the power of n, but please note that we are starting the sum at n is equal to 3 and we are ending the sum at n is equal to 11. Just a reminder, for sigma sums, I actually have to have my a and my d, or in this case my r, because that allows me to substitute into the geometric series formula. So I need to find the first 3 terms of this sequence. Because the actual series, or the sum, starts at term 3 is my a. Because term 3 is my a, I need to actually know what the value of it is. So each time I'm going to substitute in n is equal to 3, n is equal to 4, and n is equal to 5 to find the first 3 terms of this particular sum. So if you plug these 3 into your calculator, you will get a half, then an eighth, then 1 over 32. Those are the first 3 terms of this particular sequence, which actually creates our series. Great, so now that we actually have a, we can determine r because I have the first 3 terms. I still need my n for the sigma portion of this sum. A reminder that to find the number of terms involved in this actual series, I take the top number of the sigma sum and I subtract the bottom number and then I add 1. So the number of terms involved in this pattern will be the top number, which is 11, minus the bottom number, which is 3, plus 1. So you'll see that n is equal to 9. So there are 9 terms involved in this sum. Cool, everybody. So hopefully at this point you can see that I can actually do the sigma calculation because I have my A. Because I have my first 3 terms, I'm going to be able to confirm my common ratio. And because of the sigma itself, the top number and the bottom number allow me to actually confirm how many terms are involved in this sum. So now we're going to take all those pieces of information and we are going to put it into the geometric series formula. Let's go to the next slide. So we've established that the first 3 terms are a half, an eighth, 1 over 32. If you went on, you would see that 1 over 1 to 8 is the next term of the pattern. We've discussed that A is a half because this is the first term that's being involved in this actual series. The common ratio is a quarter because to get from a half to an eighth, I had to times by 1 over 4. To get from an eighth to 1 over 32, I had to multiply by 1 over 4. And because I used top minus bottom plus 1, I know that n is equal to 9. Because I have my A, as well as my R, as well as my n, I can substitute into Sn. So the sum of the first 9 terms will be equal to our half times 1 minus a quarter. This is going to be to the power of n because it's the first 9 terms, or there are 9 terms rather involved in this sum, all over 1 minus a quarter. So let's plug this all into my calculator. So we've got a half multiplied by 1 minus a quarter to the power of 9 over 1 minus a quarter. Let me just make sure that fraction comes in. So this sum is equal to 0.67 if I round to the second decimal place. Great, everybody. Let's move on to the next example. So we are given the figure ABCD, which is a square. The square PQRS is formed by joining the midpoints of the sides of the largest square ABCD. This process of forming smaller squares inside each square is continued to infinity. Let's stop right there. The second I see the word infinity, what type of series do you think this is going to be? Hopefully, sum to infinity is rolling around in your head. So the question itself has given us a clue that we need to know what the value of the areas of an infinite amount of squares would be. But let's go to the board so I can show you how to do it. So we know that AB is 8 centimeters, which means that this length is 8 centimeters, as well as the lengths of all of the other sides of this square. We know that the area would be 64 because 8 squared is 64. But in order for me to actually use the sum to infinity, I've got my A now, which is 64, but I still need my ratio. We need to find the area of the square within ABCD in order to establish my common ratio. How am I going to do this? If I know that this is 8, and we know that P, S, R, and Q are drawn from the midpoints of the sides of the square. So that means that AP would have to be 4 units, and AS would have to be 4 centimeters. Because it is a square, I know that the corners are at right angles to each other. So I can do Pythagoras to find the length of PS, and that will indicate the length of each side of PSRQ. So PS squared will be equal to 4 squared plus 4 squared because of Pythag, which means the PS squared will be equal to 32, which means the PS is equal to the square root of 32. So this side itself is the square root of 32, but if I'm finding the area of PSRQ, it's going to be 32 squared, or the square root of 32 squared, which means it's just going to be 32 centimeters itself. So because I now have the first term, the second term, if you were to find the area of the square within PQRS, you would see that it has an area of 16 centimeters squared. So I can actually see that I've got my pattern, so I can substitute in to the sum to infinity. My A is equal to 64. My ratio between each of these, hopefully everyone will agree with me, that I have times by a half, because 32 is half of 64 and 16 is half of 32. You can also use your R is equal to T2 over T1 to find this. So the denominator will be 1 minus a half, and in order to find the sum to infinity, I need to plug this all into my calculator. So it will be 64 over 1 minus a half. So the sum to infinity for the area of all of these squares added together is 128 centimeters squared. Great, everyone. I hope today's revision has helped you. I look forward to seeing you again sometime soon.